not always called B-Eng or M-Eng, so it happened to be at McGill. I think in different schools they have a slightly different designation. So to become licensed, we need to have a qualifying degree or diploma. We have to have the requisite experience. So 4 years experience is required to become licensed, and relevant experience. And we have to pass a professional practice exam. For engineers, the professional practice exam is really about law and ethics. We don't even have to pass a building code exam. It's a law and ethics exam. It's a few hours. Generally, our education is what is considered the technical criteria for our licensure. Some number of years ago, Ontario passed what's called Bill 124, which was the building code. We would get a building code BCIN number. And for a number of years, that was required in order to stamp drawings and submit a set of drawings for a building permit. The PEO appealed that, and it was repealed for engineers. So it's still out there in the world, this BCIN designation. Generally, it tends to be used by small builders on projects that don't have a professional associated with them. Meg talked a little bit about fees. There's a number of fee models. And, you know, I realized at first I was worried that there would be overlap between my talk and Meg's, and so we'd miss out on content. On the other hand, hearing the same message from two different people in two different perspectives kind of reinforces and clarifies the message. So, so we've got a number of ways that we calculate fees. As I mentioned when Meg was talking, you know, we use a table very similar to the RAIC table in our fee estimating. We base it on an 84 table, but it doesn't really matter. It's substantially the same. Our fee models are varied. The first one and the most common is probably the lump sum fee model. Anybody who says lump sum fee, I try and clarify that and say that a lump sum is really a euphemism for a guaranteed minimum fee. And as soon as you call it a guaranteed minimum fee, it sort of loses its allure a little bit. People try and insist on it. But the fact is that any unanticipated scope, if you clarify your document, any unanticipated scope, you get additional fees anyway. So the lump sum is the guaranteed minimum. We, like architects, will work on a percentage fee. So a very common percentage fee for structural engineering would be 1% of construction cost. It might range from 0.5% up to 2%, but you know, 1% as a good rule of thumb for structural engineering fees. We'll often work on a proportional fee, and I'm going to describe a proportional fee in a few minutes because it's a very, very common fee model. And then we'll work hourly. Hourly for anything where scope is not clearly defined or clearly definable, we try and insist on an hourly fee. So renovation projects, we work hourly. Custom homes, we typically work hourly because someone building their custom home, they will change continually, and so the scope is really undefinable or unanticipatable. We've started using some other creative fee fee models as well. So there was a time when it was either lump sum or hourly, and no owner would accept an hourly fee because they felt they were writing a blank check, that there was no incentive for us to ever stop working because we were getting paid for every hour. And so they would insist on a lump sum fee in order to bound our services. In our experience, we're always a little bit too busy, and finishing a project is the best thing we can do, you know. So we are naturally incented to get the job done because there's somebody else waiting for us to work on their job. But that doesn't actually translate very well to an owner who sees themselves as writing a blank check. So what we are often doing, we don't cap our fee, but we'll cap our profit. So we'll say, here's our budget for the project. we're going to bill you hourly at full rates until we hit our budget. At that time, we stop billing you at full rates and we start billing you at our cost. So there's a transparent disincentive for us to spend more than our budget. But on the other hand, our financial interest, we're not at risk. Our financial interest is protected so that we, especially on a complicated project, we can continue to providing services as the project demands because we know that it will demand and we need to be able to respond. So let's talk about a proportional fee. Generally, as Meg said, they would calculate the total architectural fee and then divide up the pie amongst the various consultants. And so often when we're writing a proposal, first off, I should say, just to put it in perspective, that the architect's scope of work is probably about 5 times the structural engineer's scope of work, or 5 times any given consultant's scope of work. What that means is that for an equivalent size firm, we do 5 times as much work as any given architect, which means that we're casting our net for work broadly. So when you're going after a project, for us to have the same odds as you in the big picture, we need to get on 5 teams to sustain we're pulling our work from the same pool of construction projects, so we need to be on 5 teams in order to just be equal to you in terms of our annual billing and scale. So the notion of the engineering being exclusive to the team is unusual. What that means to us, though, is we have to give the same fee to everybody. We're not going to give you a preferential fee versus the firm a block away. And by saying that we will not give you a preferential fee also means that we will not give him a preferential fee relative to you. So we have to give the same fee to everybody. So what we'll typically or often do is we'll say we'll give you a proportional fee. We're not going to tell you what our fee is. We're going to say here's the portion of the total fee that we're going to take, and we're going to take the same portion. Doesn't matter what architect is going after it. And what that does for you as the architect is it gives you the freedom to set your fee at whatever you think the market will bear. So if you're prepared to go in at 5% versus 6%, and that's the most competitive fee, then we're going to take our share of 5%, whereas if the other guy we would have taken our share of 6%. So that's the way that we can give you a better fee, is if you're prepared to take a lower fee. So how do we determine what our piece of the pie is? There's a well understood formula, and that is that the structural engineer will take 75% of the total fee assigned to the structural component of the work. So the rationale for that is that the architect doing the coordination of the project has a greater burden to bear than the consultants who only have to look after their own portion of the work. So each consultant takes their share of the fee, or in a way what we say is that the architect takes 1/3 off the top, and that's their fee for being the boss, for being the prime consultant and having to coordinate everybody's work. And then the rest of the fee gets divided proportional to the cost of that scope of work. So if we want to apply it, a nice rule of thumb, that the structure is worth about 18% of the total project cost, which means that the structural engineer takes 75% of 18% of the net fee. So I should describe what the net fee is. So first off, before the fee gets divided, the specialty subconsultants get paid. So, or their portion gets assigned. So if there is an acoustics consultant, a cost consultant, a kitchen consultant, you take those fees, you take them out of the pot and you set them aside for the specialty subconsultants, and then you take the balance of the fee and you divide it among the core consultants, which are the architectural, structural, mechanical, electrical, and you divide it proportional to the cost of the work. So I'll walk through an example in just a second. But here's some nice, simple rules of thumb. No one ever wants to share the rules of thumb because they're so nuanced and so varied, and the only thing I can guarantee is that these rules are wrong. But they're at least a starting point. So the first one is that the construction cost is about 80% of the project cost. So soft costs will represent about 20%. So that might be land cost, financing cost, permitting costs, fees. So that adds up to about 20%. So if you've got a project budget of $100 million, you've got an $80 million construction project, and the fee gets paid on the $80 million. It's a percentage of construction cost. Specialty consultants, about 12.5% is what we always assume, which sounds high. It sounds a little too precise when we're into decimals of percent, but in a way you can break it down this way. If you wanted to do a really simple division of the pie, you take 100% of the fee, half of it goes to the architect, half of it's left for all the consultants, including the specialty consultants. You divide that pie 4 ways, the rest of the fee 4 ways, and you wind up with 1/8 of the fee going, or 12.5% going to specialty consultants. So that's sort of a different way, approximate way to divide the pie. Structural costs, about 18% of the total project cost. Mechanical cost is about the same as the structural cost. Obviously, if you're in a lab building, it's going to be much higher. If you're in a condo, it's going to be lower. But structural mechanical are somewhere around the same, and electrical is about half of that. And if you add that up, you should get to roughly 100%. So how do we divide the pie then? If I had a blackboard, I'd walk through. Well, maybe not. It's probably not worth it. Let's just say we have a $100 million project. $100 million construction project, $100 million project cost. We have an $80 million construction cost. We're going to apply the fee on an $80 million project then. Let's say you as the architect decide that a 5% fee is what's going to win the project. So 5% of 80 million is $4 million. So now we've got $4 million is the total project cost, or the total amount of fees, $4 million. Specialty consultants are about 1/8 of that. So right off the bat, we take 12.5% or 1/8 of the $4 million. $500,000 we set aside for specialty consultants, and we're dividing a $3.5 million pie amongst all the structural, mechanical, electrical, architectural. We take 25% of that for the architect in their coordinating role, which would bring us down to, say, 2.6 million is what then gets divided. So right off the bat, about 600,000 of the 3.5 million goes to the architect for their coordinating role, and say 2.6 million gets divided amongst the sub-consultants proportional to their scope. Structural engineer gets 18% of the 2.6 million, which would be $225,000. So walk through that again. We take out the specialty sub-consultants. Then we take out 25% for the architect for their role as prime consultant. And then we divide the rest of the pie proportional to the construction cost. When we as engineers are asked for, the reason this is such an important model is that when we as engineers are asked for a lump sum fee, if you as the architect don't tell us, don't accept a proportional fee, we'll always ask for a proportional fee because it's fair. That is our fair share of the fee. And if we have a proportional fee, we're either going to make money together or we're going to lose money together. If you as the architect are fee shopping, yep.
Just a clarification. So you said that one of the rules of thumb, I think, was that 50% of the fee goes to the architect?
Yeah, so there were two, I divided the pie 2 different ways, which is unfair.
Okay, so I don't quite get, but
Yeah, so I gave you two very crude. The proportional fee is a refined model where we base it on the cost of the construction. So we net out the specialty subconsultants, we net out the prime consultant fee, and we take the rest of the fee and we divide it proportional to the value of construction. That's the appropriate and refined model. And then I said, just as a rule of thumb, the structure is worth about 18% of the total project cost. Might be 15, might be 20, but it's in that range. The other one that I said is, if you want to get even cruder, architect gets half, the rest gets divided amongst the subconsultants, roughly equally, the specialty consultants being one part of that remaining bit. So, and that's just a crude rule, take half the fee and divide it into pieces, structural, mechanical, electrical, and specialty. And that's, that's crude as can be, but at least it's simple. So what are we saying is that if the architect accepts a proportional fee, then it's fair and we're all in it together. Sometimes you as an architect will feel the need to solicit proposals from multiple engineers and make a choice based on fee. Or sometimes the owner is paying the fee and they'll ask for multiple proposals. In that case, what we will do is we'll guess at what we think the market will bear for an architectural fee, and we might come up with the 5%, and then we'll do this breakdown based on our rules of thumb, and that's how we'll come up with our fee. We'll use a proportional fee whether you know it or not. It's whether the architectural fee is based on your number or our number. Yeah. Sometimes they do, sometimes they don't. I would say that it's sort of 50-50. I kind of have a feeling that the architects that are making lots of money are the ones that don't share their fee, and the ones, if we're in the same boat, then they're transparent. A number of different ways we can set up construction contracts. So the contract between the architect and engineer is generally a very loose contract. I don't agree with Meg in the sense of signing the RAIC document. To me, detailed contracts don't mitigate risk. The risk exists. So what the detailed contract does is assign risk, but it doesn't mitigate risk. And in fact, if anything, by having a detailed contract and creating the impression that you've mitigated risk, you're more likely to be careless in a way. And to me, the way to mitigate risk is to balance it so that everybody is carrying it. And so simple agreements have the effect of balancing risk, because you know that you're all slightly exposed to each other, because you don't have anything protecting you from your colleague, who also has nothing protecting himself from you. So, in a way, it's like in a snowstorm, you're not going to go around picking up snowballs unless you think everybody else has a snowball, and then you're going to arm yourself because you're expecting a snowball fight. So I kind of feel like we're quite happy with our loose agreements, and we've been around for 25 years, and we open 800 new files a year, and we complete probably 500 projects a year, and we've done almost everything with loose agreements, and we have been sued half a dozen, maybe 10 times. Every single time, a contract wouldn't have prevented us, like a tighter contract would not have prevented us from being sued. And our biggest cost in any of the suits was not the judgment, it was the defense anyway. And so the cost, and the tighter your contract, or the more complicated your contract, the more stuff there is to argue about. So our defense costs wouldn't have gone down. So in the end, we could have invested, God, hundreds of thousands of hours in contracts. And in the end, like if I add up what it might have saved us, it'd be under $50,000, I would expect, over 25 years of practice. So yeah.
So when you say loose contract, because obviously you still have to sign something, what is involved in a loose contract rather than a more structured contract?
Well, we write a letter that says, here's what our fee is, and here's what our current understanding of the scope of work is. And that's really about it. And in fact, often we don't even do that. Often we'll just get a call and we'll say, hey, we got a project, we'd like you to start working on it. And we start working on it. And at the end of the month when we're doing our invoicing, we'll say, oh shit, we don't have an agreement. We better figure something out. And so it really is, we try and work to the demands of the project. And if the demands of the project are such that we don't have time to set up an agreement, then we start without an agreement and we figure it out afterwards. Now, we're also the least profitable engineering company in the city, so there may be a connection there. So contracts, there's a variety of ways that we'll set up construction contracts. I think you guys have covered some of this before, but I'll give you a little bit of insight on it. The design bid build model is a very common model, completely appropriate for completely normal things. So any project that has no risk associated with it, where you can find a half a dozen contractors that have built close variations on what you're about to build, then a design bid build contract is completely fine. It assigns all the risk, the construction risk, on the contractor, which is totally fine if the construction risk is low. And I'll come back to well, maybe now's the time, actually. There are dollars associated with risk. That's why insurance companies exist and why insurance companies are amongst the most profitable companies in the world, because risk has dollars associated with it. And whoever is prepared to take and own that risk is the one that's going to make the most money over the long term. So when we assign all the risk to the contractor, we'd better make sure the risk is low, because we're paying a premium to have the contractor assume that risk. So design, bid, build, very low risk projects, let's assign all the risk to the contractor. Design build projects are the projects where you put the contractor in the driver's seat. You'll often enter into design build contracts because contractors would have deeper pockets. They have the ability to self-perform, self-finance. And so they can deliver a turnkey project, which might make financing easier for you as an owner, might be one way. They've got relationships with trades, so often things can get built faster. If your program is simple and the architect is not adding value, so if you're building a hog barn and the only thing that matters is that you have 10,000 square feet of clear span space, well, you don't necessarily need an architect for that, and the contractor might be able to get it done very efficiently and really hire the architect only to get through planning and approvals. So those are situations where design build might be appropriate. The Goldring Athletic Center at U of T was done design build, and that was about expediency and about financing. So in that case, the budget was really too small for the program, but by allowing the contractor to have control, by making it a design build project, they were able to find a way to squeeze the building into the program. And then the other thing actually is design build. So when U of T gave the Goldring Athletic Center to Ellis Don, they took away all of Ellis Don's risk because they put Ellis Don in control. And what that did is meant that U of T didn't have to pay for the risk. Or they didn't have to pay Ellis Don to assume the risk because they all, at the same time, instead of giving them dollars, they gave them control. Design assist is a new model that we're starting to see, which is really appropriate for complex projects. So as skilled and experienced as you are as an architect, and as skilled and experienced as your consultants might be, we haven't done everything, all of us. And there are lots of specialty building systems available now where the bulk of the expertise resides with the manufacturer. And our first experience with Design Assist is in tensile fabric structures. That's been whether it was called Design Assist, that's been a historical model for tensile fabric structures because the expertise didn't live within the consulting community. Now I use that as an example. In fact, Blackwell, we made a very specific decision to acquire the expertise and software to do tensile fabric structures in order to give control back to designers, to architects, because we realized that all the design control lived with the manufacturers, because that's where the expertise lived. So the way Design Assist works, Design Assist is an owner will hire an architect or a set of consultants. Architect in these diagrams is a euphemism for consulting team. We'll hire a consulting team, but we'll also hire a Design Assist contractor as part of the consulting team to lend their expertise. The Design Assist contractor will help develop the design and write the specs, establish the scope of work, and establish the budget. Then when the project goes for bid, the bid documents are set up to highly favor the Design Assist contractor in winning the bid. And sometimes it's automatic that the Design Assist contractor, as long as they commit to being able to sign a contract that they will deliver on budget within the cost and deliver the product that they've helped develop the spec for, they can be sole sourced. Or in an instance where they can't be sole sourced, the documents are set up to favor them. So yeah?
What's the difference between that and CM and this? Is it just that the contractor is more closely involved in the design?
The Design Assist tends to be for a specialty subcontractor, so it's more for a component of the building than the project as a whole. Now the terms I'm speaking of come from the point of view of a subconsultant, and we are one step removed from the contracts. So whoever has given you the talk on this before would know much more than I do about exactly how these contracts are set up. So I'm giving you kind of the perspective of a subconsultant on this. So we're seeing Design Assist for a subcontract as opposed to the general contract. And yeah?
Does this subcontract then, is in actuality two contracts, one for the assistance in design and one for the actual bid?
That's right, yeah. And so sometimes the design fee, I guess the design fee gets rolled into the subcontract to execute the work if the Design Assist subcontractor is successful. If they're not successful, then they get paid the fee. Now sometimes they just get paid the fee in advance, but often it'll just be rolled into the execution cost.
And the second contract is just a stipulated subcontract?
Yeah, that's right. I mean, it could be set up in any way, I guess, but a stipulated sum would be a normal way to do it because they've participated in doing the design and writing the spec. The scope should be very well established. There's no risk left for them, so a stip sum would be fine. I think I know what you're saying, and I think the answer is yes. So they would write in pre-qualify the design assist. If they can't sole source it, they would pre-qualify the design assist subcontractor and list them as an approved supplier. And then the general contractor would bid. They'd be obliged to get a price from the design assist subcontractor. If they want to go get a price from somebody else, then as part of the process, they have to qualify their alternate. And that has to happen during the bid process. And generally that there's a reasonably tight timeline for them to qualify an alternate. So they can't just submit an alternate and qualify them after the bid. They have to qualify them during the bid. If they haven't pre-qualified their alternate, then their bid is rejected. And then it sounds like you've dealt with construction management. We see construction management as highly beneficial for, particularly for fast-track projects, because it allows the certain parts of work to proceed in advance of other parts of the work. And the construction manager is being paid a fee and can solicit bids. They don't have to have all their bids in place in order to get get started and get engaged. So it allows things to happen sequentially. Really, it's very difficult in a STIP sum to do any kind of sequential bidding because the STIP sum has to be based on everybody's bid. A real shortcoming from the engineer's perspective in fast track or sequential tenders is that we have to then prepare our drawings for issue in advance of everybody else. And there's a huge amount of work coordinating with mechanical and architectural that happens very late in the game. So we're naturally tendering an uncoordinated set of documents, and then picking that up as changes after the fact.
Are you speaking about the foundation package there, and the structure has to come first, or?
Well, it could be a variety of packages. So sometimes the foundation package gets issued in advance. Sometimes foundation and structural steel. Sometimes all of the structure goes out before the mechanical and architectural are finished. And so coordination gets picked up as changes, and the changes have a cost associated with them. What we really try to advocate in a steel building, for example, is break the steel into primary and secondary steel. So primary steel is columns and beams and joists and deck. But we don't do any of the secondary steel that's required to support mechanical units and windows and door frames, and all of the stuff that's required to carry the envelope is secondary steel. We don't capture that in the first bid. So primary steel gets bid early, and sometimes the bid will include a unit rate for secondary steel where they have to give us they just provide a tonnage number. Or sometimes secondary steel will get bid out as a second package. That's a little bit problematic because you run the risk of having two steel subcontractors. And then integrated project delivery. This is the one that everybody wants to talk about. We're really just seeing it starting now, and yet it's been talked about ever since Revit came around. It's been a decade we've been talking about IPD, or integrated project delivery. So the idea is that with integrated project delivery is that you want everybody to collaborate and remove the adversarial environment in which we currently operate. And to me, that's a matter of how you allocate risk, and the way that's so. I've had some sled dogs, and a sled team is a really good analogy for IPD or for collaborative approach. If you take a bunch of sled dogs, a bunch of feral husky dogs, and you tie them together with ropes and attach them by the neck, and you have this as your aspiration, good luck. What you're going to get is this. You're going to get a bunch of furry dogs and blood flying as they start to fight. Because just tying everybody together doesn't mean that they're going to collaborate. If you're forcing them together in the same environment that they're used to, So what IPD relies on is trust and experience. You have to know the people you're working with in order to trust them, in order to collaborate, because you need to understand and believe that they have your interest at heart, and you need to have their interest at heart, not just your own. So what are the fundamentals of integrated project delivery? The first one is you have to change the nature of the contractual relationship. So if you just say, here's the team, I want you guys to collaborate, and we're going to call it IPD, and it's all going to be great. But by the way, here you have to sign the same old contracts that where all the risk gets downloaded to you. Then you're going to act exactly the way you always did, because you know that your interest is not protected by your collaborators, and nothing's going to change. So one of the key elements is forming a new legal entity, a new corporation, which the owner, the architect, and the contractor are all shareholders in a new legal entity. So they are acting literally and legally as one entity. The nature of that contract, I don't know. We haven't actually done it, but I know that that's a key element of it. You need to change the leadership structure. So one of the great benefits is that in IPD, whoever has the most knowledge, experience, and broadest perspective on any given decision is the one who takes the lead on that decision. So when it comes to architecture, it's the architect, but when it comes to construction, it's the contractor. And then we need to make sure that everybody's speaking a common language, and the common language is BIM. So this is you know, I know that there have been successful projects. It's not easy. BIM is not a panacea. You know, the Goldring Athletic Center, the contract with Walter Steel was that they would be provided with a BIM model to work from. And it wasn't in our contract, and we didn't prepare a BIM model, so Ellis Don hired somebody to prepare a BIM model. The person who prepared the Revit model used our documents, basically modeled exactly what we drew, and gave it to Walters to fabricate. It wasn't useful to Walters at all, because it didn't capture the level of accuracy that Walters needed. So when Walters said, we want a Revit model to work from, what they meant is that you, general contractor and consulting team, do all the dimensional coordination so that it is geometrically 100% resolved, and give us that, and we'll base our price on having that, and we'll take care of all the connections and means and methods. What they got was something that was a 3D version of a conventional set of drawings, and it actually wasn't useful to them. They still had to start from scratch, build a model, coordinate every dimension. So BIM's not a panacea. If you're building a BIM model so that you've got a nice 3D image, that's one thing. If you're building a BIM model that will be used for fabrication, that is actually a different thing. Our work is governed by a professional practice guideline published by the PEO. The only one we have was published in 1998, and we still go on it. It outlines a number of things, including what the documents are to contain. But I'll start with kind of a motherhood statement that the purpose of the documents is to convey all information that is not obvious to an experienced builder. So we're not preparing a set of IKEA furniture assembly instructions. We're relying on the builder being experienced, and we only show what is not already obvious to them. So for example, we don't dimension bar lengths on our reinforcing steel drawings. We show the size and number of bars because that affects scope. The scope is not obvious to the builder. But the bar lengths are governed by the Reinforcing Steel Institute of Canada's Manual of Standard Practice, and nobody knows bar lengths better than the detailer, and so we let the detailer figure out bar lengths. We need to show configuration, we need to show dimensions, because those are not obvious. And we need to show non-typical details. But we don't tell a steel fabricator how to connect an open web steel joist to a steel beam. They know how to do that. They've done that 1,000 times. I should say that John, actually, you remember this is maybe even better than I do, but that our industry was hit by a terrible recession in the early 90s. It decimated the industry. There was nothing for us to do for seven years. I think I am probably the only 50-year-old engineer in the city because everybody else, nobody in my generation got a job in engineering. The impact of that, and that was right when AutoCAD came in. So before that, everything was hand-drawn. So when things started to happen again in the late 90s, there was an extremely junior workforce that was using technology that was unfamiliar to the senior workforce, and in a way they rewrote the rules because they didn't know the old rules. So what was my point? Oh yeah, so at that time we had it. I remember I was guilty of this myself. We had a tendency to overdraw everything. That a whole generation of people didn't know what they could count on the contractor knowing, and so we overdrew everything. Part of it we could because we were using CAD, and it was easier to make changes and copy details. So we over-documented everything. At the same time, everybody in the construction industry retired, and we had a whole new wave of contractors who probably didn't know anything. So what happened in the early 90s really completely changed the way we as an industry worked. We used to rely a document set, I'm sure that the old timers will tell you, a document set for a project which was 12 drawings in 1988 would be 60 drawings today. So here are the phases of the job: schematic design, design development, contract documents, and contract admin. These are the phases as outlined in the AIA and OAA standards of practice. These are the phases that are outlined in the engineer standard of practice. So they don't quite match, but they kind of match. So our preliminary design is more or less schematic and design development. Final plans and specs is the CD phase, and then we have general review during construction, which is what you call contract admin. We don't actually administer contracts as engineers. You guys do that as architects. We review construction for conformance with the contract documents is the limit of our role during construction. Costing has yet another breakdown. So we have Class D costing, which is indicative costing, which is generally just based on square footage. We have elemental costing, which would happen more or less at the schematic design phase. Substantive costing happens at the design development phase, and then pre-tender costing, Class A, happens at the contract documents phase. So 3 different professions, we all have 3 different ways of saying really the same thing. I'll walk through just a few highlights. So here are the highlights of what it is that we include as structural engineers in our documents. They have to bear a stamp. They have to convey the purpose of the drawings, so issued for permit, issued for construction. The codes that govern the drawings. We have to describe the materials. Any design information. So we have to say if we've designed for 1 kPa of wind load and we've designed a roof for 1.2 kPa of snow, we have to actually document that on our drawings. We have to indicate any special provisions of the structure, so future use. We have to show information about any existing structures, and we have to show derived dimensions, structurally derived dimensions. This is a really important one because we don't show every dimension on the structural drawings. We only show the derived dimensions. In our current practice, if we cut a section, we'll show a dotted line that describes the outside of the building envelope, for example, and we'll show here's how far our structure is from the building envelope. But because that's the derived dimension, how far that structure is from anything else that's the prescribed dimension. We want the edge of the beam to be 125 millimeters back from the face of the brick because that allows the insulation and the airspace. And the brick is described by, where the brick is described by you, the architect. You set that. So we don't actually say where the edge angle is. We say where it is relative to something. That's the structurally derived dimension. And then we'll show other things that are not obvious. So we as structural engineers don't dictate sequence of construction. Construction starts from the footings and works up to the roof. That's obvious. And so we don't describe that. But we do describe sequence of construction if it's not obvious, and if we need to dictate it because the structure requires it to be built from the roof down for some reason. We might describe things like dewatering requirements only if they affect the structure. When it comes to footings, yeah? We write the structural component, yeah. In fact, even on jobs with a designated spec writer, rarely do they write the specs for the sub-consultants. So the designated spec writer would write the architectural sections, but the sub-consultants would write their own. That's right, yeah. Footings, we need to document the obvious. What are the footings? How big? Where are they? And then some of the things that are less obvious. The only place on a job that we would show insulation, for example, as a structural engineer, is where we require it to frost protect a footing because it's too shallow. We haven't found it deep enough for frost. And then we'll document things like interferences. So we wouldn't show where buried surfaces are unless it affects the positioning of a footing. Framing plans, we describe configuration and sizes. That's the obvious thing. That affects the scope of work. We also have to document the forces. Because the steel detailer has to detail the connections. We don't tell him how to connect. We document the forces so that he can determine how to connect things together. Similarly with columns, size and configuration, of course, but we also have to specify the loads. Specifications, here's the list of things we cover in our specs. Scope, standard and codes, material, workmanship. Those are our material specific items and they belong in our spec. There are a number of other things according to the standard of practice that need to be covered in our specifications that are potentially in conflict. So submittals, quality control, temporary works, anything to do with the working relationship and warranties. Those are all things that exist in Division 1 of the spec. So you've seen the various spec divisions. Division 1 is really the contract. All the other divisions relate to materials and they're very material specific. It's workmanship, it's detail, things like that. Division 1 is the contract, and Division 1 is your spec as the architect. So there are things that we're required to cover according to our standard of practice that really belong in Division 1. And so we need to coordinate those carefully with you. Generally, you should cover them in Division 1, and we should just make sure you've covered them adequately. Sometimes you do get overlap. We'll cover these things in our own spec sections as well. So here's what we do when. This is actually important. I tried to skip over that. Schematic design phase. We identify the system and the general configuration. So we need to decide at schematic design, is it a concrete building, is it a steel building, is it a wood building? We need to develop the approximate member sizes. So you need to know if we're dealing with 2x12s or 2x8s in a floor framing because that affects you as the architect in setting your building height. You know, the thicker the floor structure, the taller the building has to be. So we need approximate sizes that allow you as an architect to move your work forward. So we're only providing the sizes that affect what you're doing at schematic design. We have to do sufficient calculations to demonstrate the feasibility. So we can't get railroaded down the road by promising you could do an 80-foot transfer at the ground floor of a 72-story building. We have to actually verify that it's possible. And we need to provide enough information for the Class D cost estimate. Schematic design is largely qualitative. So we're giving you information and developing the system based on our experience. At no time in an engineering project, typically, and I should almost not admit this, but at no time are we doing quantitative comparisons of multiple systems. That's not in our normal scope of work. We make those decisions qualitatively from our experience. Design development, we verify our schematic design. We determine quantities for all major repetitive elements. So, we have our primary beams and joists and slabs. We work out quantities at the design development stage for those. And we do that because the next stage of cost estimating has to be much more detailed. They need quantities for that. We develop our standard details. So, so our standard slab edge condition, our standard roof to parapet condition. We do that because your next job is to start developing your wall sections. You've developed your building sections at schematic design. You're starting to develop your wall sections, and you need to understand how the structure fits in. So then we do the other work that's required for the other consultants to advance their work at the appropriate stage. Yep.
I'm not sure if you have worked on a lot of P3 projects, but in a P3 situation where you're doing a cost after the schematic design, how do you sort of ensure, because it's less specific, like you're not verifying the schematic design?
Yeah, we just have to qualify, and we have to insist that the contractor who's carrying the bid carries an appropriate risk number. So we have to be very careful because it's schematic design. We haven't done all the design, and yet they're committing a hard number, and so they just have to carry an appropriate contingency. But there have been engineers successfully sued because of a contractor underbidding based on incomplete information. So it's actually a problem. You know, so it's really about clarity of making sure they understand what the information is. In fact, I can tell you that we almost got sued for big bucks by Elliston on the Gold Ring Athletic Center because they committed to a price based on schematic design. We had no rebar shown on the drawings. They took a guess at a quantity and way undergassed. And they thought that was our fault. They were looking to our Arizona emissions insurance as a source of funding to cover their shortfall. They didn't end up suing us on that, but we were skirting close to the line for a while. Contract document stage, we coordinate all our dimensions and we develop all the exceptions to the details. So at DD, we've established the driving details, the standard conditions, and then during the contract documents, we extrapolate and develop all the derived conditions. And then we have to do all our work. So anything that doesn't affect anybody else, everything that affects everybody else, we tried to do at design development. But all the stuff, writing our spec, doing all the calculations for all the members nobody cares about, that's all stuff we do at contract document phase. Construction phase, we have two functions. We have an office function and we have a field review function in the field. Our office function at the construction phase is to review shop drawings and answer questions. That's really it. We can break it down into those two things. Shop drawing review, it's important to understand what we do in shop drawing review. In shop drawing review, we are reviewing the drawings for general conformance on a sampling basis for general conformance with the contract documents. So we don't check dimensions, we don't check calculations, we don't even check every member. It's the contractor's responsibility to get it right. We check enough to form an opinion of generally whether the drawings are right or wrong. The checking of dimensions is your responsibility as the architect to check dimensions if the things that are important for you, because we're not prescribing dimensions, we don't check them. You as the architect are prescribing the layout, it's up to you to check the layout. Certain things, the things that are highlighted or with an asterisk, we do on request. So we have a job during the construction phase to support you as the prime consultant where we have expertise that exceeds yours, but we're not administering the contract. So we'll review extras if it's outside of your expertise. We'll review schedule if it's outside of your expertise, if there's something that we have to offer beyond what you do. Yep. Sorry, we do which? No, we don't draft them. So what we do is we draft instructions, but because we're not administering the contract, the actual instruction comes out of the architect's office. Now, what will often happen is that we'll have a structural CCN or a structural site instruction that we supply to the architect that gets an architectural site instruction or CCN cover put on it. To me, that's a bit confusing, because you wind up with a dual number system. We have our number system, there's your number system. Essentially, the contract, it has to come out of the architect's office. And so what we try to do is we just have structural instruction, and that will get a CCN or an SI cover from the architect's office. When we do field review, we're checking a sampling of the construction that's completed to monitor the contractor's quality control and to satisfy ourselves that they've correctly interpreted the drawings. That's what we're doing. We're not the quality control, and so we don't check everything. Obviously, the more problems we find, the more we check. So we do a sampling, we advise the contractor. Our responsibility is to advise the contractor, provide written reports, follow up deficiencies that we have identified, and attend any relevant meetings. So we don't come to every site meeting, we come to only those site meetings where the structure is being explicitly discussed. If we find that a contractor is not performing, then we need to go to the owner and we need to say, normal field review isn't adequate for this project because your contractor is underperforming. You, Mr. Owner, need to impose a quality control measure on the contractor. The contractor is being paid for it, so they should pay for it. If it has to be someone from outside of the contractor's own agency, then the contractor pays it back to the owner who might pay it. That might be a consultant, might be the architect or engineer, or preferably it's a third-party inspection company. Yep.
So if you're not checking everything when you review, what would happen if you, I guess, missed something and then later there was a structural problem as a result of that?
Right, so that's a really good question. So our argument would be the contractor built it wrong whether or not we caught it, and the contractor was responsible. And probably in the formal language of the contract, that's the case. The engineers have been found liable because if we go back to the duty of care, we are responsible to provide the service that a reasonably competent practitioner working in the same environment on the same kind of thing would do. And so if the thing is found to be egregious, then, and something that we should have caught, then we'll wind up bearing liability for it. So if we're going out to the site every 2 weeks and the contractor is screwing everything up, but our contract is to go every 2 weeks, well, a reasonably competent engineer would be put on notice that things are going wrong and would put the owner on notice to do something about it. Because as the engineer, we have no relationship to the contractor, no contractual relationship. We have no power of force. We can't do anything other than advise the owner that he needs to do something. So if we're found if it's something egregious that we should have caught, we will wind up bearing liability for it, even though it's the contractor's responsibility to get it right. We wouldn't be liable for the repair because the contractor is still responsible to get it right, but we could be found liable for the impact of not having repaired it in a more timely fashion. So other services that the engineers can provide but are not in the normal scope of services are listed here. The one that I want to draw your attention to is architectural works. So architectural works are stairs, handrails, canopies, facade, structure within the facade. It's things that are structural in nature, but not an integral part of the building structure, are considered architectural works. They're not in the scope of work, the standard scope of work of your structural engineer. So where does that leave you as an architect? Because you sometimes need those services to be done. So here's where it leaves you. You either do nothing, in which case you will get only what is obvious to the builder. So if you say a handrail per OBC, then they'll give you a handrail and it'll be a 2-inch pipe with a 2-inch top rail and vertical pickets every 4 inches, because metal fabricators know how to build handrails, but you'll get the obvious handrail. If you want to design it, then you need to be able to describe the scope, and you'll need feedback on the scope. What generally happens is you'll ask your structural engineer, and we'll be nice guys, and we'll give you some advice. We'll give you some qualitative feedback, and we'll do a few calculations, but that information will live in your documents for architectural works. Or you can add that scope of work to the engineer's scope of work. So often a feature stair, for example, will be added to the structural engineer scope of work to design and detail, even though it's in the architectural works. And we're always, as structural engineers, we're delighted to do that stuff. It's just you don't know it's coming, and so it's not part of your base fee. You can't anticipate it. So it'll wind up coming after the fact. Alternatively, you hire another engineer to look after architectural works. So my wife's company is there to do architectural work. She's a structural engineer, she does architectural works, and she's working on guards and stairs for the Senate building with Diamond Schmidt right now. She's doing the architectural works, there's another engineer doing the building itself. The other thing that's not in our scope of work is value engineering. Value engineering, and I put an asterisk beside this because it's not really value engineering. We're doing value engineering all the way through the project. We're evaluating, we're doing it qualitatively. We're not doing it quantitatively unless we can't figure it out, but generally it's qualitative. Value engineering is a euphemism for cost cutting after the fact, and that is not in our scope of work. That is an additional service. So I'm going to show you a few projects because of their interesting contractual, the interesting way that they were handled contractually. The first one is the Bergeron Center for Engineering Excellence at York University. This was a building that was designed by Arup Partners. Blackwell was hired to assist in the facade. So this is one of those ones where the architect, I believe, asked Arup, help us with the facade. Arup said, this is architectural works, it's not in our scope of work. And so the architect came to us and said, look, we're going to assign this development of the facade to a design build contractor. I want you to come over and have lunch with me, give me a few napkin sketches so that we can write a terms of reference for the design build contractor. So we did that, and we had a meeting, and they said, boy, this is a little more complicated than we thought. Can you work out in detail one section of it so we can give that to the design build contractor? And so we did that, and then the construction manager, Lang O'Rourke, who were fantastic to work with in the end, said, look, we think, based on what you've given us so far, that it's advantageous to not do this package as a design build, but to divide the substructure from the cladding component. So this is what we gave them. This was sort of round 2 after the napkin sketch. We said this is how we do it. We'd break it up into 20-foot long panels, fabricate each one in a way that accurately defines the window size and location, and then install those in the field with 6 degrees of freedom adjustment. So then they said, we agree with this, but we think it's advantageous from a cost point of view to subdivide the work between a steel fabricator doing this scope of work and the cladding contractor who would do the windows and cladding, rather than having it as a design build. So they asked us to do a set of contract documents. So now we were engaged as the structural engineer to do a conventional set of scope definition contract documents for the facade work based on this. So we did that. And then in the meantime, my wife Shannon suggested it would be really beneficial to you for us to give you a 3D model of this that then the fabricator could build from. And the idea was that if we can take all of the dimensional coordination risk away from the fabricator, first of all, this is a classic example where there's big dollars associated with that risk. So we take the risk back and we give the money back to the owner. So we save a pile of money by giving them dimensionally coordinated model. The other thing is we could start building that model while during the bid process. So we had a 4-week head start on that 3D model, and by the time the fabricator was engaged, we could hand them a fully coordinated 3D model of all the structural steel that was required for the facade, which was that. And in the end, this is, we have been told anecdotally that this is what saved the facade. They were at risk of losing the facade, which was the key design element, because of cost. The big dollar numbers associated with the facade were risk numbers, not material numbers, not labor numbers. And by taking that back and taking back all the risk and handing them a fully coordinated 3D model, took back all the risk numbers and made it feasible. And the steel fabricator made a bunch of money on this. Like, they actually did very well on it. So this is sort of an example of integrated project of delivery at a sub-trade level. So not an overall project, but where you take one subcontract and you redivide the pieces based on who's best able to deliver them. This is our very first effort at, I added this slide while Meg was talking because she was talking about working with Gregory Ryback, and this was our first effort at any kind of integrated project delivery where we redefined the various roles. It was done in a very ad hoc way, but we were working with Levitt Goodman, who are awesome. You guys know them, obviously. And I got a call from the project architect saying, we want to design into the project a longhouse, but we want it to be a contemporary interpretation of a traditional longhouse. Do you have any ideas? And I had seen work by not Richard Croker, from Dow, Rural Studio, and Ted Kavanaugh from Dow, who had done this amazing dining pavilion using a lamella reciprocal frame structure. I thought, well, that's really cool. It would probably be completely appropriate. So we worked out a way to wrap the lamella around the spherical end. The only way I could think to convey the information and sort it out is with a 3D CAD model. So I did a 3D model in AutoCAD, if you can imagine. And I gave it to the architect, said, what do you think of this? They gave it to Gregory Ryback, said, Gregory, what do you think of this? Do you think you can do it? He just took our 3D CAD model and built it from that. We never did, I don't think we did a few calculations to demonstrate that it worked, but I don't think we did a single drawing for this. We just handed over our 3D CAD model and Gregory built it and did an amazing job. They had never built anything like this, but he was just confident that he could do it. This project, our first major tensile fabric project, was this one was a design assist model. And in a way, this is not a success story. it's a tremendous success story in the sense that it got built. The scope expanded and expanded. It was originally supposed to be just the pavilion on the end, which was a stage cover. Got expanded to be an audience cover in the design phase. By the time construction was finished, they wanted to add sidewalls into a full enclosure, and we're going back this year to add acoustic treatment. Few lessons on this are, one, if it's a really good idea, it will always take on a life of its own and be more than you expect. And this is what Kenora's finding is that as soon as they had it, the demand for the facility became so high that they needed to dramatically broaden its scope. So from being kind of a fair weather concert venue to the kind of community hub. And really they underestimated their ambition for it. But the other thing is, so this was Hildeman Thomas Frank, landscape architect, or Frank Cram, landscape architects, didn't know anything about tensile fabric structures other than that they wanted one for this band shell. Went to Tensile Integrity, who are a builder, and said, we need you to help. This is a design assist project. And without critical design feedback, without enough knowledge to give critical feedback, what we wound up with is kind of functional and unique looking, but in a way really could have stood some design critique. I don't think this would have passed a first-year studio review as a design project, and could have stood it. But because the expertise wasn't there to provide appropriate critique, we wind up kind of down this road, and you wind up with something that looks unique, but it just kind of a bit big and weird. The next, yep.
Did you get hired on a certain point? Sounds like you weren't there to start.
Well, we were actually, but we were hired by the contractor who was there leading, the fabricator who's leading the charge. So they were making the design decisions, and we were there. You know, the historic role for this was that the engineer in a tensile fabric structure would do calculations and put a stamp on something. It wouldn't even draw anything. And it would be drawn by draftsmen that live in the manufacturer's office. So it happened that we have a fantastic and collaborative relationship with this fabricator, and we could have had a lot of input, and we could have brought our architect friends in to give us critique, and we could have done a lot of things. We didn't because that's not the traditional role, and it was early in the days for us. But our next project, this one, same fabricator. The fabricator started with this kind of weird two-cone thing that really looked like a brassiere stretched out between two chairs, and it was not attractive. And we said, hey, maybe on this one we could raise the bar a little bit from a design point of view and do something more interesting. And so this one there was no landscape architect. We were working directly for the fabricator, but we weren't afraid to sort of share some ideas, and did this, which is really a tensegrity system. I don't know if you guys have ever encountered tensegrity, but tensegrity is when you have compression elements that are floating in a cable net that don't actually connect to another compression element. So you can see we've got that big floating king post. And rather than having big tripods, we put a compression ring around the outside. So other than the fact that I think that this might just be a little bit too low for the context, we think this one was quite successful. And again, this was integrated design. We worked directly with the fabricator and contractor on this one. So I'm going to leave you with that. Does anybody have any questions? And we've probably gone a little bit over time, but oh, right on time. Look at that. Well, I do appreciate that you've been asking them during the lecture, because as Meg said, that makes it a lot more interactive and a lot more fun for everybody.
Okay, well, thanks, Dave, very much.
Okay, John?
So,
clear, so we'll do, the exam will be